azimuthal average.
It is very interesting that any radial advection is a heat source, heating term. But it is interesting to know that where is the source of heat.
Yeah, no, I agree. It would be interesting to see where that ultimately comes from. But yeah, so this kind of leads into a couple slides I have that it might not answer your question, but it just conceptually makes the idea maybe a little more clear. Like, what is eddy radial advection? So if we imagine, so this is just a schematic of the white here is the eyewall and the blue inside is the eye. And so if you look at the terms, the eddy radial advection has to do with the flux of potential temperature, the eddy flux of potential temperature and its horizontal convergence. And so what this means is that we have an asymmetry in the temperature or the potential temperature field, and if we have warm air on one part of the on the edge of the eye and cold air on the opposite side of the eye, but not in the center, we can warm the eye if we have the radial motion correlated or anti-correlated with the potential temperature perturbation. So if we have a flow across the eye, an asymmetric flow, and so from west to east here, then on the west side of the eye, this flow represents a perturbation inflow, so U prime is negative. And if we had warm air here, then theta prime is positive because this is warmer than the average around the eye or the eye wall. And then on the other side, if we imagine we have this cold perturbation region, so theta prime is negative. And if we have the asymmetric flow in the same direction flowing across the eye, we have this is now on this side of the eye. This is now a perturbation outflow, so U prime is positive, and so now U prime theta prime, the product is going to be negative, and so the tendency from that is now going to end up being a positive tendency, and so from the convergence of the eddy flux. And so if you have this type of structure where you have this anti-correlation between the asymmetric flow and the potential temperature perturbations, you can transport systematically warm air from the eye wall region into the eye, and you can warm the eye through this mechanism. And we can see this by looking at the horizontal cross-section of the simulation. I believe this is at t equals 36 hours. I don't remember 100%, but this is in the middle of the time that I just showed you the budget for. So these are horizontal cross-sections. This is a 160 by 160 kilometer box, and the black circles are just range rings every 10 kilometers radius. And then the white lot contours here are the vertical motion at 6 kilometers, so that's showing where the eye wall is. And the upper left here is the potential temperature at 6 kilometers height. So the warm core here is close to the center, but it's actually offset. So the warmest air is actually not right over the low level pressure center. And so if you look, this is the total potential temperature. So you could take the azimuthal mean of that and then subtract the total, and you would get the perturbation potential temperature. And that's what this asymmetric theta on the upper right. So we have warm air, relatively warm air on the southwest, and relatively cold air on the northeast. And then if we look at the asymmetric radial velocity, you tend to have some regions of inflow in the same region where you have asymmetric warmth. And then this positive asymmetric radial velocity, so that's perturbation outflow, so it's bringing air out of the eye into the eye wall, that's correlated with this region of negative asymmetric theta. And so that the product U prime theta prime is going to be negative in both those regions, and so the convergence of that is going to be a positive tendency of potential temperature. So where the eye is, where the eye wall interface region, where it's warmer, you're bringing that air closer to the eye, and where it's colder, you're bringing that air away from the eye, and so you end up with a net warming tendency of the center of the eye from this. So it's kind of related to the fact that you have you're starting with a potential temperature distribution that's not centered on the center of the eye, and you're making it more axisymmetric, and you're warming the center of the eye at the expense of the region of the outer part of the eye.
So tropical cyclone with asymmetric structure is more likely to have warm core structure in the middle troposphere.
I don't think I would say that. I don't think we know. I'm saying in this simulation, you have an asymmetry during this period of rapid intensification, and that's I guess the axisymmetrization of that asymmetry is allowing you to warm the center of the eye. But I don't know that if that weren't occurring, you might have warming there might have been more descending motion, and later, the period of strongest warming, you actually do have very strong tendency from mean vertical advection. So yeah, I don't think we know. So you're saying that possibly more asymmetries leads to more mid-level maximum, but I don't think we can answer that from this. You need more simulations and more analysis.
And the other question is, can you go back to the advection figure? No, just you showed. This one, yes. And do you think this kind of structure follows the shear-induced instability?
What do you
there
mean?
is, like, for example, that the vortex Rossby wave is kind of follows this structure of temperature and wind field can follow the vortex Rossby wave features, or do you think?
I don't know.
Why they have this kind of structure? So maybe the structure should have some relationship with some instability, usually, typically, right? So in that case, maybe this kind of shear between eye region and eye or region, horizontal, radial direction can induce that kind of mixing, right?
That's possible. I honestly, I don't know the answer. I'm not sure whether that's the case.
But I think you can check you can just plot the PV patterns, and maybe you can analyze them. Maybe we can. If I'm genius, maybe I can check from these figures, but I myself do not know at this moment. But I think if you could sometime, maybe you can analyze the structure of this asymmetry, contribution.
Yeah.
But there's no pure symmetric structure
No pure symmetry.
in a real
I'm not
world.
saying that,
But to some extent,
of
all
course,
tropical cycles have some asymmetric structure, like
So-
wave number one to
right.
something.
But basically, of course, the simulated one is, of course, the mixed feature, right? They should exhibit a mixed feature, but I myself suspect that this comes from this kind of horizontal distribution can determine the main part of the structure. So yeah, I also do not have a clear answer to the question.
I will say, I think the fact that that the temperature or the potential temperature is maximized, is shifted from the low-level center, is probably indicates that there's a tilt of the center with height, which is very common in weaker tropical cyclones. So I think
Okay.
having a tilt of it contributes to allowing you to have large tendencies from the eddy radial evection.
Okay, so that's
So the
it
reduction,
means maybe vertical
Yeah.
coherence can explain.
yeah. Although I think some people have expressed like the tilt in the form of vortex Rossby waves as well. I'm not as familiar with that, but
Research
yeah.
papers or other
Yeah.
papers.
But yeah, so I guess my suspicion would be that if you had a significant tilt to the vortex, and that as you intensify the storm and you reduce the tilt, there probably would be a significant tendency from the eddy radial advection. I think there maybe would have to be, kind of by definition, if you were organizing the center to become more vertical. So, yeah, I guess I would guess that an intensifying storm something like this could be common, is my guess.
Do the white contour indicates updraft?
Yes, yeah, so that indicates the updraft is 6 kilometer. I think it's 1 meter per second.
Maybe here is the most intense convection over there, so the storm might tilt this way because it has very intense convection.
It could. This simulation has no shear, so there's not going to be a preference to tilt one way or the other. But yeah, when it's weak, it could still tilt. If there's convection on one side that's stronger, it could tilt towards that. Yeah, I agree. But yeah, it's clear that even though the warmest air is away from the center, it's not in the eye wall. It's still in the eye. So it's So yeah, I guess the answer to the question about where that warmth is ultimately coming from for the asymmetric mixing, I think it's probably coming from subsidence that's warming the area in the eye but away from the center, and then the asymmetric radial motions are rearranging that to bring that warmer air closer to the center.
Does your result, it mainly result on the PBR scheme? You said you use Yonsei University
Yes.
PBR scheme for the tropopause layers?
Well, the YSU scheme will have a vertical diffusion tendency at all heights, yes.
So how about maybe you use the WAF, and WAF
Yeah.
also has Merayama Jijonjak scheme. Did you use that?
I haven't used that. Yeah, I don't know how that would differ. But I suspect that doesn't make too much of a difference for this because the tendency here is very small, and I think it should also be small in an MYJ scheme too. So I don't think the PBL scheme is contributing much to the above the boundary layer at least. So I was showing you why I think in the simulation you tend to get the maximum at mid-levels. But why do we see two warm core maxima, that middle level one and that upper level near tropopause one? And so I think we can understand the existence of two maxima somewhat in a somewhat simple manner by just considering the evolution and the shape of the mean vertical velocity field and the static stability field within the eye. So I've showed you this before, so this is every 12 hours, starting from the beginning of the simulation. So it's averaged 12-hour mean vertical velocity, and then each consecutive 12-hour period from left to right, and then top to bottom. And so the bottom here, bottom right would be the second half of day 6 of the simulation, so 120 to 100 or 132 to 144 hours there. So that's when the storm, at the bottom here, this is when the storm is very intense in a category 5. The budget periods that I showed you are these 3 periods, and you can see there's some consistent features to the structure of the mean vertical motion in the eye. The strongest descent in the center of the eye tends to be in the upper troposphere at about 11 to 12 kilometers. And during the period of rapid warming, which are these 3 periods, it's on the order of a couple centimeters per second, maybe up to 5 centimeters per second. With time, you get concentrated subsidence on the edge of the eye wall and the eye. And as I mentioned, that subsidence doesn't contribute much to warming because of the very strong evaporative cooling you get in that region from precipitation. Within the center of the eye, the dry region, you get the largest subsidence at about 11 to 12 kilometers height. But you don't have the largest warming there. The strong warming that you're getting is up at 14 kilometers, so a couple kilometers above that. And you're actually having close to a minimum in the warming in the region where the subsidence is strongest. And that's because the amount of warming that you get from subsidence is dependent not just on the magnitude of the vertical velocity, but on your static stability profile. So if you're strongly stable, then there's a large vertical gradient in potential temperature, and you can much more easily have large warming for the same vertical velocity. But if you have a weak static stability, your theta contours are far apart, and the tendency you get from the same amount of subsidence is weak. And if we look at the static stability, you'll see, the red colors are strong stability and the blue is weak static stability. And the weakest static stability is in the upper troposphere at about 11 to 12 kilometers. So the region where you have the strongest descent is the region with the weakest static stability, which means that for a given vertical velocity, the potential temperature tendency you can get is small. And so that's why we can't get large warming in that region. We can get large warming in the tropical tropopause region. So where the static stability starts rapidly increasing in the tropical tropopause layer at about 14 to 16 kilometers, for even a small amount of sinking motion, you can get a tremendous warming. And you can see we still have some weaker subsidence at about 14 kilometers. That's sort of the top of our layer of sinking motion here during the period of rapid warming and intensification. And so because of that, you can, if you go back to the potential temperature change, that's why you get a really strong maximum there, is because the static stability is really large and you still have some weak descent. And then the mid-level maximum in the warming, so early on we might have some ascent there, but even later in the period of strong warming, we have descent here, but it's weak. It's only a centimeter, 2 centimeters per second, but we can get large warming there because we tend to actually have a maximum in the static stability in the middle troposphere. And so it's this maximum in the static stability that allows us to create a maximum in warming there for a broad region of weak subsidence. And you tend to have some type of mid-level maximum in static stability even in the initial condition. And that initial condition comes from the Dunnian environmental mean sounding from observations. So the mean tropical environment has a static stability profile where you have a weak mid-level maximum and then decreasing stability above to being very weak static stability in the upper troposphere, and then having a rapid increase in static stability in the tropopause layer. And I think it's that static stability structure of the mean environment that results in the structure of warming we see. And again, the key is that very weak stability around 10 to 12 kilometers means that you can't get much warming, and so you get a minimum in warming there, even though you have very strong descending motion there. And so then you, on the either side of the minimum, you can get the mid-level maximum and then the near tropopause maximum. And so this just clarifies that this is the this is a 12-hour change in potential temperature, and then this is the tendency from mean advection, mean vertical advection, and again, this mean vertical advection is given by W bar d theta bar d z, so it's dependent on the vertical structure of the vertical velocity, but also the vertical structure of the potential temperature or the static stability. So for this time, again, we see, well, there's some points under here, but less warming is accomplished at the level of peak subsidence, which is 12 kilometers. You don't get much warming there. It's in a region where there's the minimum. And then at the top of that, you get large warming because the static stability n squared is very large there. And at mid-levels, you also have a maximum in the static stability. And even though the subsidence there is very weak, less than a centimeter per second here, you're still able to get large warming because the stability is high. So any questions about this?
I just wondering the center of the storm has updraft.
At low levels, there's an up. Yeah, there's weak upward motion in the mean at low levels in the boundary layer, and maybe very near the center, a little bit above. Yes.
Where the air parcel come from for the updraft? The descending
Well, there's.
boundary
I think you
layer?
tend to get weak boundary layer convergence from friction in the eye, and you'll have inflow coming from the eyewall into the eye, and you tend to get some weak convergence in the eye, and that's consistent with the photo of the eye that I showed from Hurricane Katrina and from many other cases. You tend to get low-level clouds in the eye, so below the inversion, there's some weak vertical motion upwards. So I think that this structure is relatively common. I think we don't really know how often we would expect to see this in observations. There's a lot of variability, but I think a number of other studies have also found evidence for this, including this nice paper from Ono and Sato.
Excuse me, do
yes.
you know the Ono is Ono?
Yes, yes. So I like this figure a lot, and correct me if I'm interpreting it wrong, but I think he found that this white line is the minimum pressure, so showing the time height plot of the perturbation temperature at the center of the tropical cyclone, and you early on during rapid intensification have the formation of a mid-level maximum here at about 8 kilometers, and then I believe that the black line is the tropopause height, and you tend to get near tropopause warming that happens only when the storm starts to become rather strong, and that's I believe similar to what I found in my simulation, that the mid-level warming tends to precede the upper-level warming. In this case, the upper-level warming became much larger, and the warm core became strongest at the upper levels, and the mid-level warm core kind of disappeared and merged with the upper-level maximum. So there's a variety of structures in different simulation studies, but overall, I think there's the commonality that you tend to get both a mid-level maximum and a near tropopause maximum at various times during the simulation, and sometimes at the same time. And I think there's a number of other recent studies that have found some similar structures. I'm just showing another example of more recent observations of the warm core. This is an analysis I did from Hurricane Patricia, which was perhaps the most intense hurricane ever observed. This was flown as part of the TCI field campaign. So there was a WB-57 aircraft flying at about 19 kilometers and dropped dropsondes into Hurricane Patricia at over a 4-day period. And I'm showing the last two flights on October 22nd, 2015 and October 23rd. And on the 22nd, Patricia was a rapidly intensifying storm that was already a Category 4, 115 knot storm. This is the perturbation temperature here. The zero contour is the red line. There's a lot of noise and uncertainty here because it's observations, and observations are messy, and there's missing data in some of the sondes. But you can see there's evidence of a clear mid-level maximum, about 4 to 5, 6 kilometers maybe, of warming in the eye, and then there's a secondary maximum, really about the same strength as the mid-level maximum, well up at 16 kilometers. And this is in the base of the tropical tropopause layer. So the tropopause here, I have indicated in the magenta line, that's the cold point tropopause. So just below the coldest temperature is this maximum in the perturbation temperature. So you get very large warming here. That's consistent with the simulation, forming a really strong maximum there in the region of large static stability. And there's a recent paper by Patrick Duran and John Molinari in, I think, JAZZ, published a couple months ago, where they did a nice analysis of the tropopause structure and how that changes with time, and they find evidence for large vertical mixing of the tropopause, and it's a very interesting study. So here, my point is that we have this observation of an intense, rapidly intensifying storm with two maxima near tropopause and mid-levels. And then on the next day, 24 hours later, Patricia was 160 knots. It was actually rapidly weakening at this time. There was an Eyewall replacement cycle, and the inner core was collapsing, but it was still a strong Category 5 at the time that it was observed. And we have this feature at 7 kilometers. I'm not sure it's real, but there's sort of a broad mid-level maximum here of perturbation temperature. And again, we have this near tropopause maximum at about 15, 16 kilometers. So, yes?
What is the definition of perturbation temperature in this?
Oh, in this analysis? Let's see, what did I do? I took the average of some dropsondes that were several hundred kilometers from the center to define the environment for this analysis. So I think they were around 400 kilometers from the center.
And dash line means the path of job zone.
Yeah, so the dashed line is just to indicate that is those are locations of the dropsondes that made this analysis. So there are, I don't know, like 15 dropsondes in here. And yeah, I'm just plotting it at the mean radius of the dropsonde. So the radius might change with time, but I'm just plotting it all at a constant radius to make it possible to make a cross section, and that's the mean radius. So so there's a couple here that are very near the center that really go into making the center structure.
In total, how many drop don't they do this time? How many drop don't they?
For the flight, or for this analysis?
Yeah.
Well, I'd have to count them. I think there's about 20 in here, maybe 20 or 30.
I mean, including the references.
Oh, the reference dropsondes?
How many? Just in order.
And for this flight there were 80 dropsons about. But the flight went to much larger radius, so this in here is like 20 or 30 dropsons in this. So they were dropping sons about every 5 kilometers.